Hi everyone, I'm Liang Qingren from the University of Kansas. It's my pleasure to present our research, PrivDNN, a secure multi-party computation framework for deep learning using partial DNN encryption. This project is a collaboration between the University of Kansas, Delft University of Technology, and the University of Missouri, Kansas City. I will start with the background. Nowadays, machine learning is pretty much everywhere. In particular, when we have a classification problem, we can almost always find a pre-trained model and adopt it for the problem. However, not all model owners are willing to open source their models, because the proprietary model may be trained with large amounts of private data. The model itself could be a valuable asset to its owner. On the other hand, although the model owner may provide machine learning as a service, the data owner may not want to ship their data to the model because the data may be sensitive, such as the medical or financial records. So how can we run inferences while keeping both the data and the model private? Encrypting them sounds like a straightforward solution, but how do we perform inference with the encrypted models or data? This is where homomorphic encryption comes in. Homomorphic encryption lets us add or multiply encrypted data with other encrypted data or plain text. Specifically, fully homomorphic encryption allows unlimited additions and multiplications, and the CKKS scheme supports calculations on floating point numbers. With homomorphic encryption, a typical privacy-preserving machine learning solution looks like this. The data owner encrypts the data, sends it to the model owner. The model owner receives the encrypted sample, performs inference in the ciphertext domain, and sends an encrypted output to the data owner. The data owner decrypts and learns the label. This sounds great, except that homomorphic encryption is very, very slow. For instance, CryptoNet is the first to use homomorphic encryption to protect data, but it takes 50 seconds to classify a batch of tiny amnist pictures. That's way too slow to be practical. Meanwhile, the data owner benefits from the approach, since she learns the classification result without disclosing her data. However, the model owner has to pay the price of highly expensive computation. The model owner has no incentive to do this. To tackle this problem, we introduce two ideas. Idea 1, we use homomorphic encryption to protect the model and send the protected model to the data owner. This way, the model owner can offload the calculations to the data owner's side. Idea 2, we encrypt only a subset of neurons instead of the entire model to save the computation. Here is an overview of the PrivDNN process. During initialization, the model owner selects core neurons and encrypts them. Then, the model owner shared the partially encrypted model with the data owner. This initialization is a one-time process. During evaluation, the data owner performs the inference with a batch of inputs and gets intermediate results with some ciphertext. Authorized users can send those cipher results to the model owner for decryption, and then continue the inference to get the classification results. Before introducing the details of PrivDNN, let's take a look at how DNN inference works in plain text. Since the model is plain, all the operations are plain as well. We feed the model with plain input and get a plain result. To be clear, we will call this original model inference accuracy, A sub O. In PrivDNN, we will select a subset of important neurons to encrypt. We call them the core neurons. The other neurons will remain in plain text. So the inference computation will be split between the clear text domain and the ciphertext domain. We need to slightly modify the structure of the model so that the output of ciphertext neurons are not sent to clear text neurons. Authorized users can send the final ciphertext output to the model owner to decrypt. Then, she can continue the DNN operations with the decrypted values to get a classification result. In this case, our first goal is to make sure the classification accuracy for the authorized user is very, very close to the original model accuracy. On the other hand, unauthorized users cannot decrypt the ciphertext outputs from the encrypted neurons. The only way to complete the inference is to drop those ciphertext outputs. Our second goal is to ensure that the classification accuracy for such unauthorized user is significantly lower than the original accuracy. In practice, when the accuracy decreases by 10% to 20%, the model is considered useless. The third goal is about performance. Since cipher operations are thousands of times slower than plaintext operations, we must minimize the number of operations in the ciphertext domain. That is, to minimize the number of core neurons. To evaluate how well we achieve our goals, we design a score to measure the quality of our core neuron selection. The first part is a penalty for the decrease in authorized accuracy, and the second part is the benefits of the decrease in unauthorized accuracy. In PrivDNN, the most important question is to select the core neurons based on the objectives. Selecting core neurons from all neurons is a combinatorial problem. For very small models, we can try all possible selections and evaluate the model accuracy for both authorized and unauthorized users. Let's take a look at an example of the LeanNet model on the MNIST dataset. LeanNet has two convolutional layers, and if we select 2 neurons from the first layer and 6 from the second layer, there are 120,000 possible combinations. We tested all these selections and showed the distribution of A sub S and A sub R. According to our goals, a good selection should have high authorized accuracy and low unauthorized accuracy. The best ones are shown in green, and the worst ones are shown in red. Unfortunately, it's impossible to check all selections for large models. Therefore, we propose 4 selection algorithms. In the random selection, we randomly select the required neurons from the model. In the greedy selection, we select neurons that best achieve our goals. Specifically, we test each neuron by adding it to the core neuron set and evaluating the selection score. We then permanently add the neuron with the best score to the core neuron set. Then we repeat this process until we have the required number of neurons. The pruning algorithm removes unimportant neurons from the model to reduce the model size while maintaining the model performance. So the remaining neurons should be the important ones. Thus, we aggressively evoke the pruning algorithm to remove a large number of unimportant neurons, and then use the remaining ones and the core neurons. The pruning plus greedy algorithm use the pruning algorithm in a less aggressive manner to reduce the size of selection pool, and then apply the greedy algorithm to make the final selection. With the ground truth, we tested the performance of our 4 algorithms, and we can see in 18 different scenarios, the greedy algorithm identified the best selection in 13 scenarios. Even in the worst case, it found the 7th best selection out of all 120,000 possible combinations. We use 2 static and 2 dynamic pruning algorithms. The static algorithms run very fast, but give less satisfactory performance. However, dynamic pruning runs slower than the greedy algorithm and performs worse than the greedy algorithm. Hence, it doesn't make sense to use dynamic pruning. When we compare the greedy algorithm to the pruning plus greedy algorithm, the greedy algorithm always performs better but runs slower. So there is a trade-off between the selection efficiency and selection performance. In practice, the users may decide which option they would like to use. Finally, we will talk about performance improvements. The computation of privacy-preserving DNN inference relies on the number of cipher operations. Here we show the number of ciphertext and plaintext operations of PrivDNN with 4 different models on 5 different datasets. For each bar, the green one is the number of plaintext operations, and the gray one is the number of ciphertext operations. In general, PrivDNN saves the model inference time by 85% to 97%. depends on the size of the model. At the same time, fewer cipher operations also means less memory. So PrivDNN also reduces the memory consumption by more than 97%. Here is the conclusion of our work. We present the first practical framework that can execute DNN inference while keeping both data and model private. We propose 4 algorithms to identify the core neurons and demonstrate the effectiveness of our prediction using 5 popular datasets and 4 models. We achieved up to 30 times speed up in homomorphic encryption model inference and reduced memory requirements by 97%. We would like to thank our sponsors. We also like to thank the anonymous reviewers and the chefs for their valuable comments. Thanks for listening. I'm happy to take any questions.